Right. Question number 2. Consider a bus line that spans 10 stops, including the initial and terminal stops at each bus stop along the way. The bus stops if there are people waiting at the bus stop to get on the bus. Otherwise, it continues its journey without stopping. So I have 10 stops. So let's say this is 1, that's the initial stop. Number 2, number 9, and stop number 10. So this is the initial stop. This is the terminal stop. And that's it's the understanding that the bus will definitely stop at the initial and terminal stops. It's at the initial stop because it will start this journey there, so it will be initially stopped there, and the terminal stop because it will finish the journey and it will come to a stop there. So the stops in between 2 through 9, the bus will stop if there are people waiting at the stop to get on, or if there are no people waiting, it will not stop at that bus stop. At each bus stop along the way, the bus stops if there are people waiting at the bus stop to get on the bus. Otherwise, it continues its journey without stopping. For simplicity, we assume no one on the bus gets off before the terminal stop. So this is to avoid scenarios where there are no people waiting, but there will be some people who wants to get off, so the bus will have to stop there. So I mean, you can ignore people that want to get off. That's the idea. So the question in part A is, how many different journeys can the bus take depending on whether it stops at each bus stop or not? So how many different patterns can you have where, let's say, stop number 2, it does stop, stop number 3, it doesn't stop, stop number 4, it doesn't stop, and so on. So how many patterns are there in such a way? So I'm assuming it will definitely stop here, it will definitely stop here, but in each of these, stop or doesn't stop. So which gives me two choices here, two choices here, two choices here. Therefore, I'm going to have 2 to the power 8 different patterns, let's say. That's 256 different journeys. In how many of these journeys the bus stops at stop number 5? So stop number 1, you will stop. Number 2, 3, 4, 5. You want to stop here. 6, 7, 8, 9, and 10. That's the terminal. You will stop here. And two choices here, two, 2, and 2 choices here. 2 to the power 7. That's 128 different patterns, different journeys. And the final part of this question, X1, X2 through X9, random variables representing the number of passengers getting on each bus stop. We will assume all passengers get off at the terminal stop. So no one is getting on at the terminal stop, obviously. So we don't have X10. And PK is the PMF of each of these X's, indicating the number of passengers to get on at each stop. And we assume these are all IID, independent and identically distributed. And here's an example. Let's say P0 is 0.1. So that means 10% of the time, or with a 10% probability, no one is going to get on. And P1 is 0.12. That's the probability of one person getting on. And 0.18 is the probability of 2 people getting on, and so on. Describe, but do not compute, how to find the probability that the bus reaches the terminal stop with 36 passengers on. So 36 is, well, I want 36 to be the sum of, well, let's say I from 1 to 9, the sum of xi's. Let's denote this with a y. I want to find the probability that y equals 36. This is the question. So if I have the distribution of y, I can answer this easily, but obviously I'm not given the distribution. And theoretically speaking, we have the distribution of x's, but this here is just as an example. It's not, we are not going to solve this question based on this given distribution. This is only a demonstration. But the question is, how can I, or what is the probability that I will reach, or the bus reaches the terminal stop with 36 on board? So we need to find the probability that x1 plus x2 plus ... x9 equals 36. So two approaches here. One, if you have the distribution of x's, you can just try to list all the combinations that add up to 36. So for instance, 2 plus 0 plus 4 plus 1 plus 5 plus 0, ... So all 9 stops, you assign numbers that add up to 36. But you have to do this for all possible combinations of numbers assigned to each 9 stops that make up 36. So this is extremely tedious to do and next to impossible to accomplish on pen and paper. So you can do that using computers, but there is a much easier way if you have access to a computer. Suppose that, well, you are given already P of K is the distribution of each of these x's, and I want their sum. And I know that they are all independent. So remember, if I write the generating function, so let's say g of z as sum of I from 0 to infinity, P of I times z to the power I. That's the generating function of each of these distributions. And if I want to find the generating function of y, their sum, what I need to do is just raise the generating function to the power 9. This will give me the generating function of y. So let me differentiate that with g sub x of z. And this will give me the generating function of y. And if you do want the distribution, you can take the inverse transform. But you are only interested in this probability. So look at this. Look at the coefficient of z to the power 36 in this generating function, and that will be your answer. Okay, so it will comprise all possible scenarios where the x's add up to 36, and that coefficient will give you, well, the sum of the corresponding products of the corresponding probabilities, and that will be your answer. The probability that the sum of these 9 x's will add up to 36 is going to appear in the coefficient of the term z to the power 36 in the generating function of random variable y.